Reminder on you have no school Monday. You guys have no school Monday. And then Tuesday is a day that I won't be here. That's not me taking advantage of a 4-day weekend. I promise you I have a dental procedure I have to have done. So I won't be here on Tuesday. And that's the day you're going to work on your online quiz. It's in College Board. Bring your notes. Bring your laptop. You can work with each other. You can work with your notes. And again, I will make sure my sub knows that you're allowed to talk during this quiz and look at your notes and stuff like that. I'll keep it open longer than just that day, just so you know. So if you don't finish, and I forgot, it's like roughly a little less than a week or something that I keep it open. Or if you're absent, you don't finish it, or you forget your laptop, you're out of luck. You're not going to be able to do the quiz because it's online. So just, I think most of you bring it every day anyway. But if you don't normally, just make a note to yourself that you need to bring it on Tuesday, okay? So we're going to start 1.9, 1.10 today, and we'll go back to it next Wednesday, right? And we're still in rational functions. We have each day added a little bit more and a little bit more. We started with end behavior, then we did horizontal asymptotes, slant asymptotes, inequalities, and today we're talking about vertical asymptotes and holes, okay? These graphs, as I've told you, are kind of complicated. They have so many parts to them. Every graph looks different from the one before, so that's why we're taking many, many, many days and many, many, many sections to cover them. And so having said that, please make sure if you're not here one of those days, some of you were absent yesterday, I make these videos for you to review, like you really didn't understand what I was saying in class. You paid attention, but you're half asleep or whatever. Or if you're absent, you need to go back and review. Please make sure you watch those because they really will help you stay up to date with what I'm doing because you can't really miss anything in this class because you're just going to get really far behind. All right, done talking. What the big takeaway yesterday was zeros come from our numerator, right? If we set our factors in our numerator equal to 0 and solve, those are our x-intercepts until they're not, okay? So what we're going to talk about today is what happens with the numbers in the denominator. So you can look right here. These are two examples of rational functions. We know they're rational functions in algebraic form because it's a fraction, okay? We know they're rational functions in the graph because they've got those curvies called branches, okay? And what we haven't really talked about too much in depth is what is going on in those denominators. What we should know is that you can never divide by 0. You can never, ever have a 0 in your denominator. That's wrong. It's like a number one rule of math. No zeros in a denominator. So when you have an x in your denominator, you have to remember that that means there's a number x can't be. What can x not be in this problem? 2. Okay, we know from just every math class, every, fiber in our math being that our denominator cannot be 0. In this particular problem, 2 would make our denominator 0. Therefore, x can't be 2. Okay, fine. Now, I also reminded you or taught you the other day that a graph is a picture of a function. So if it's going to represent this function, something has to show up on my graph at x equals 2 to show visually that 2 is not one of my solutions. Those come up as holes or VAs. Holes or VAs. If you are in the denominator and you don't cancel with an identical twin factor in the numerator, you are a VA. So in this graph, we have a vertical asymptote at x equals 2. You can see it. It's right there. It's a point on the graph that our branches can't touch. It's like it's happily going along, and then there's that imaginary line that stops it from going toward touching it or crossing it. So it makes a turn, and it just goes up forever. Okay. Same thing with this branch. As it goes towards the, to the right, it's going to get blocked by that asymptote, and it makes it turn and go down. So think about that. Okay, so we have a vertical asymptote at x equals 2. How did I get that 2? Let me just make sure you guys understand. I set x minus 2 equal to 0 and solved it. Okay, obviously you don't have to show that work, but in case somebody doesn't get it, I want to make sure. So 2 would make my denominator 0. Okay, Now, look at this one. I can look at my denominator and say x cannot be 3 or 2, right? Those are my two numbers that would cause a problem for me because it would give me a 0 in the denominator. We can never divide by 0. So, you know, what we learned yesterday is going to kind of contradict what I'm about to tell you. Because remember what I said to you yesterday, if you're in the numerator, you're a 0. We would have a 0 at 3 and a 0 at 1. But if we have common factors on the top and the bottom, in other words, if my 0 on top gets canceled with the denominator, it's no longer a 0. It's a whole, okay? So, or a VA. In this case, we would have a whole at x equals 3, okay? Now, if I simplify this, that's 2x minus 1 over x minus 2. After I cancel that out, that's the simplified version of this rational function, right? That's the simplified version. So sometimes the question will say, what is the x value of the whole? It's at 3. But a whole, and you can see it right here, is an actual ordered pair. It's a literal open circle on your graph. It's called a point of discontinuity because this is continuous. I don't have to pick my pen up to keep drawing this. Here, I would have to pick up my pen and then jump over the hole and keep going. Discontinuous, the opposite of continuous, a point of discontinuity. So if they ask for the actual ordered pair, so you just have to read the directions. So in our homework, sometimes it just asks for the x value, so you'd be done. If it asks for the actual point, I mean, you could pull it off the graph, right? It's 3, 4. But if you didn't have the graph, you would plug the 3 in here and here. So 3 minus 1 is 2, 2 times 2 is 4, and 3 minus 2 is 1, so you would get 4. So I know I did that really fast, but anytime you want to find a y value and you have the x value, you can just plug the x value in. The key is you would always plug into the simplified version, not the original. Because if you plug a 3 into the original, you're going to have a 0 in your denominator, and you're going to have this situation. So you always plug into the simplified version. Okay? Then we say, all right, so we gave 3 a job, right? X equals 3 as a whole. 2 needs a job. Okay? He's a bad guy, too. He has to be shown on the graph as a place your graph doesn't touch. Since he's left over in the denominator, notice he didn't cancel with anyone. That makes him a VA. Can you have a whole without a VA? Yes. Can you have a VA without a whole? Yes. Can you have multiple wholes and or multiple VAs? Yes. There's no rule about, oh, you must have one of this. It just depends on the function. As I've told you, these graphs are different from one to the next. So we're just going to be evaluating all of this stuff. Okay? And you can see there's that x equals 2 right there. All right? So what happens if, well, let me just say, again, if you cancel, you're a whole. If you're left over, you're a VA. Those are the two things you can be. If you are a number in the denominator, you have to be either a whole or a VA. That's it. There's no exceptions to the rule. It's one or the other. But what happens when we have multiples? In other words, multiplicities. So I'm going to try to, I'm going to kind of use this space right down here to kind of expand that. Now, you don't have to write this out. Maybe just do the first one with me. Because I'm only going to do this on the first one because it gets kind of obnoxious. This h of x, I'm just rewriting it. Instead of using that multiplicity with a 2, I'm going to actually write it out. So you can see why we use the squared symbols instead of writing it all out. But those equal each other, right? They're the same thing. So what we would ask ourselves, so what the question is what are my VAs and wholes, okay? So first step, whether you write it or not, I don't care. We should know that x can't be 4 or 5, right? Again, we only look at the denominator. X can't be 4 or 5. A 4 or a 5 would make a 0 in my denominator. Everyone agree with that? Good, good, good. Okay, what job do they have? 4 and 5 are either a VA or a whole. You have to be one or the other, okay? So we tell by looking for matching factors in the numerator or not. So x minus 4, look what we have. We have 2 of them on top and 1 on the bottom. So I can cancel these 2, right? If you cancel, you are a whole. Remember, we have to give 4 a job. Even though there's an x minus 4 left on top, that does not matter. X, we're going to have a whole at x equals 4 because we have to give him a job. Remember I said, if you are in the denominator, you have a job of either a whole or a VA. If you are no longer in the denominator, who cares what's going on top? If you are no longer in the denominator, you are now a whole. Okay? This x minus 4, even though it's left in the numerator, it's going to have an open circle at 4. Okay? Because the denominator is going to dominate the numerator. Okay, let's look at the x minus 5. We have an x minus 5 here and an x minus 5 here. So if, this is confusing, look, if this x minus 5 weren't there, if it was just one x minus 5, that would be another whole, right? But we have a x minus 5 left. We canceled one, I know, but remember, everyone needs a job, and what you're about to see, I'm going to show you a very cute little picture, is that vertical asymptotes are the boss of everybody. They trump everything else. If you have a number left in your denominator, even if you canceled, it is always a VA. Here's the picture I was going to show you. And this, so that's an actual picture of my son. Just kidding. He's a really big bodybuilder dude. Not that big, I'm just kidding. So this is a great visual of vertical asymptotes are the boss. So even if you canceled something, the vertical asymptote, if it's in the denominator, that is the one that overpowers the whole. And both of them overpower the x-intercept. Okay? So vertical asymptotes, then wholes, then x-intercepts. Okay? And so that's why this x minus 4 is no longer an x-intercept, it's a whole, because we canceled, okay, in the denominator. So really, it's all about what's happening in the denominator is a good way of looking at it. What's happening in the denominator, okay? Look at this next one. I'm not going to write it all out. Let's look at a couple more of these to kind of make sure we understand it. So I know x can't be, only in the denominator, -2, 3, and -4. Those are the 3 numbers that are bad, and they need a job. They need to be either a VA or a whole. So let's start looking. X plus 2's cancel. So we're going to have a whole at x equals -2, because we canceled. There's no longer a -2 in the denominator. It makes you a whole. How about the x minus 3? Canceled again. It's going to be 3. Whole, another whole. You have more than one. It's okay. And look, there are 6 on top and 2 on the bottom, right? So all 2 of these are going to cancel. How many are left on top? 4. Is that going to be a whole or a VA? Nope. It's all about what happened in the denominator. They all cancel. If you cancel, you're a whole. We got 3 wholes. So if it asked you for VAs, you'd say none or NA. Let's look at one more. X can't be 0, 1, or -3. 0, 1, -3. If you are an X, you have a 0 attached to you, okay, a value. So if you set X equal to 0 and solve it, you get 0. If that were just like a 2, it wouldn't be part of this, okay? So does X cancel with anything on the top? Is there another X or 2X or 3? No, there's no X on top. That means we will have a VA at X equals 0. We gave the 0 a job. How about X minus 1? Does X minus 1 cancel with anyone? Nope. You're going to have a VA at X minus 1 because it's not going to cancel. It's left in the denominator. And if you don't cancel, you're a VA. And then X plus 3, there's 1 on the bottom, 2 on top. So this one will cancel, and that will leave 1 on top. That means it's a whole. Everybody gets a job. So focus on the denominator. What's happening in the denominator? If I canceled, I'm a whole. If I'm left, I'm a VA, no matter what is going on top. Okay? So let's actually do just a couple problems. This is the main thing of what today is all about. So if you're getting it, that's great. First period was really confused. I blame myself, not them at all. Okay, so looking at this, I know x can't be 3 or 4. X can't be 3 or 4. So let's see what type of job we're going to give them. X equals 3 is left, right? It doesn't cancel. X minus 4 cancels. Like if I simplified it, that's what's left. Since it's left in the denominator, x equals 3 is a VA. The one that canceled would be a whole. And again, if they wanted the ordered pair, I'm not going to waste the time. I would plug the 4 in right here. 4 plus 2 is 6. 4 minus 3 is 1. I guess I just did waste the time, but you get the idea. I could plug 4 right here, and get the whole ordered pair. But it just asks for the x values. Okay? X can't be 1 or negative 3. 1 or negative 3. Those are the problems. Let's see what type of problem. Cancel that one. 1 left over. Cancel one of those, right? Like my simplified version would look like this after I cancel everything. So if you're left over in the denominator, you are a VA. If you got canceled, you're a whole. Are we starting to get it? Important, very, very important. Sometimes we're not factored already. We need to factor example C's denominator. And first step of all factoring is GCF. Now, we're not dealing with imaginary numbers anymore, so don't worry about that. That's as far as you can go. Now, I think you guys would agree that x equals 0 is a problem, right? And it doesn't cancel, so we're going to have a VA at x equals 0. That's the y-axis, x equals 0, okay? So in order to make a 0 here, think about it, guys. X squared plus 5. In order for that to equal 0, this would have to be a negative 5, right? Because negative 5 plus 5 is 0. What can I make x squared that will make it a negative 5? Trick question. What can I square and get a negative 5 from? Doesn't exist, right? There is no problem with this x. This x actually is not a problem in our denominator. There's always exceptions to the rule, right? Because if I solve it, I would get an imaginary number. And we're not dealing with imaginary numbers anymore. So in this case, that is the only problem. 0 is the only problem. So be on the lookout for problems like that. What could I plug in here to make a 0? It would have to be a negative 5. There's no way to square something and get a negative. It's impossible. It doesn't happen. All right, and then last one of these, that numerator is the difference of two squares, x plus 3, x minus 3. And my denominator is a chart problem. We're looking for the two numbers that multiply to get negative 6, add to get 1. Where's my good factorers? 3 and? Good. Positive 3, negative 2. Good job. Okay, so x can't be negative 3 or 2. Guys, you have to know how to factor. Remy does. Okay, got to know how. It's not going away. You can see it just pops up. I'm like, okay, factor this. You can't be like, I don't know how to factor. We have to know how to factor. Okay, so x can't be negative 3 or 2. Let's simplify this. Those cancel. That makes it a whole. X minus 2 is left over. It's a VA. Okay? If you cancel, you're a whole. If you're left over, you're a VA. You don't cancel. Okay? That's memorization. Know it. Cancels, wholes. Okay. We're going to use our graphing calculator here in a second. Let me factor this denominator real quick to make a point. Okay, if I factor the denominator, I know x can't be negative 1. So it's asking what values make the denominator 0, negative 1, right? We know that's the problem. Let's see what it looks like, though. Do me a favor, though, and clear your RAM. If you don't, you're not learning anything because the last period already typed it in for you. You need to know how to type a rational function in. So clear your RAM, please. Second plus 712. Go up to y equals. And when you put this in, you have to put your numerator and your denominator in parentheses. That's really it. So it's in parentheses x minus 1. Close the parentheses. And then divided by, and you could do the factored version or this one. I think this is easier. It doesn't matter which one. X squared plus 2x plus 1. Oh, notice I forgot the parentheses. Guys, if you don't want to have to type everything in, there's an insert button. It is above delete. And I'm going to insert a parentheses, and that way I don't have to type it all again. All right, and then hit graph. Now we could zoom in a whole bunch and see what's really going on here, but I want to show you how you can use the table to really help you. Okay, so you can see there's two branches kind of like around that. We already know at x equals -1 there's a problem. Look at your table. If you go up to -1, you see where it says error? That means there's an asymptote at -1. So x equals -1, we have a vertical asymptote. It says error. And then right on my screen, I see two really good points. I see an x-intercept and a y-intercept. I see an x-intercept at 0, -1. I see a y-intercept at 1, 0. And that would give me this branch. These graphs are pretty hard to graph because they're very curvy, so we don't graph a lot of points. Just a few points, and then we just kind of estimate the curve, okay? But look at what the left-hand side is doing. So the left-hand side will be the numbers less than -1. So if I scroll up, look, they're all less than 0. They're just all going to be below. And that's what makes these graphs so weird. They're not always symmetrical. It's not like it's going to look exactly like that on the left side and the right side. That's what makes these graphs tough. There's so many different things going on. Okay? So what I want you guys to notice is that around this value right here, what do we notice about the graph around the value of x that makes the denominator 0? So at x equals -1, what are all my output values doing? They're going down forever, decreasing without bound. That means going down towards -infinity, okay? Just trying to remind you of all the language. So what we're going to learn in this last little bit here is whenever your graphs are going towards a vertical asymptote, they're either going to go up forever or down forever. So you're either going to be going up towards infinity or down towards -infinity. So what we're going to learn about is something called a one-handed or left and right-sided limits. So far, next page. So far, our limits, when we have written this, had to do with end behavior. And that still exists. And so we would say as x approaches -infinity or +infinity. What I want you to pick up on in this example here, in these notes, is that we can approach anything. A could be any number in the whole world. And in this lesson, it's going to be the number that is your vertical asymptote. And that little negative means from the left, and that really little plus means from the right. So think negatives are on the left, positives are on the right. So using this graph as an example, I could say, what is, and I'm just going to write it really quick, you don't have to write this. What is the limit of this graph as x approaches -1 from the left? As my graph comes from the left, what are my y values doing? They're going down forever. Same thing from the right. As I approach -1 from the right. Now this goes against everything we've learned. You always read a graph left to right. But in this case, we're saying from the right, what are my y values doing? As I get closer and closer to x is -1, we're also going down. Okay? And that's what we're going to see in our last example. Oh, so sorry. Sorry. So let's put a whole bunch of that. Our final example, which is example 3. Let's put everything we just learned together in one problem, and then I'll get you going on your short homework. Okay? Stay with me. I know it's Friday. It's hard to think of all your classmates sitting at home sleeping while you're in here doing this. But they're going to have to catch up, and you won't. Okay. So we're going to answer a bunch of questions. Use the equation for f of x and the graph of the function to answer the following questions. So we're given a rational function. It's already factored for us. Thank you. Let's remind ourselves that x can't be plus or minus 3, right? Plus or minus 3, those are the numbers that are going to cause a problem. So where are we going to have a vertical asymptote and a hole? Let's just go ahead and put both of them together. So if you cancel, you're a hole. So we'll have a hole at x equals 3, right? That's the number, 3. That would give us a 0, and that's the one that canceled. And we'll have a VA at x equals negative 3. So I think we run that into the ground, right? If you cancel, you're a hole. If you're left over, you're a VA. Okay. And you can see that right on the graph. There is that vertical asymptote. There is a hole at positive 3. Okay? We're just writing the x values. For values of x near and less than negative 3, what are the output values doing? So what they're saying is, look, watch my pen. For the values of x near and less than this, they're talking about this piece. What are the y values doing? They're going up, right? So we are increasing without bound. Code for towards positive infinity. What about the other side? What are these x values doing? They are going towards, decreasing without bound. Moral of the story is, as your graph, your branches approach a vertical asymptote, the y values are always going to go up forever or down forever. Okay, always. It's like it stops it. It's this like force field. As the graph is going, it's like, oh, I can't go any further. I'm going to have to turn and go somewhere else. Same thing on the bottom. It's going to hit that wall. Can't touch it, but it gets close to it. It's like, tells it it can't come near it. All right, let's do a few limits. What is happening? So this is going back to what we learned yesterday. So some of you weren't here for horizontal asymptotes. We have a horizontal asymptote right there. So what is the limit of the graph as x goes to the left towards negative infinity? What is the y value that we're approaching? You're almost there. Remember we called our horizontal asymptote end behavior asymptote? Sometimes they call it that. It's 3. Right. If it were negative infinity, this asymptote wouldn't be here. It'd keep going down. And that's what we've seen in all the days before rational functions. But since there's an asymptote there, a horizontal one, it stops you from going down. It means you're going to get close to 3, but you'll never touch it. Same thing in the other direction. We're going towards towards positive infinity, and our y values are going as close to 3 as it can. It will never cross and go up forever. It stops it. A horizontal asymptote stops your graph from going up and down. A vertical asymptote stops your graph from going left and right. Okay? Horizontal asymptotes give us our end behavior. Okay, now what about approaching negative 3 from the left? So here's negative 3, right? It's that line. What is our graph doing as it comes from the left? Infinity. It's what we said right here, just another way. And from the right, our y values are going towards negative infinity. That's what we said right here. Okay? So that's kind of new. You have to be able to look at these graphs and evaluate what it's telling you. What are the x's and y's doing at that part of the graph? Okay. All right. Find practice set 1. Somebody tell me the page number. Thank you. 101. I don't have page numbers. All right. So all you're doing, let me show you, 1 through 6, you're just stating the VAs and the holes, the x values of them. Number 9, I think will be self-explanatory. And then when you get to 11 and 12, all I care about is find the holes, VAs, and the zeros. And you'll see it when you get to it. But let's do the first one together. Okay, so 1 through 6 is like what we've been talking about in every problem. What are the VAs and what are the holes? So x can't be plus or minus 1, right? What type of problems are they? Well, did you guys write down the assignment? I feel like I'm all over the place. I'm sorry. Maybe you haven't written it down yet. I apologize. Okay, so x can't be 1 and negative 1. If you cancel, you are a whole. If you're left over in the denominator, you are a VA. Okay? So the x plus 1 is left over. That's why we have a VA there. And that's all you're doing for those problems. Okay. Mm-hmm. Mm-hmm. I think it's 10. I'm pretty sure it's 10 questions.